I welcome you all to this Indo-Swedish workshop on clean coal technologies for India. Let me just share my uh, presentation. Let me go on to slideshow mode. Sachin, can you tell me if I am on the slideshow mode? I'm on the first slide.
It's not visible yet.
Are you seeing my first slide?
I can see it. I can see it.
Okay.
Now
Sachin, is it okay?
yes.
It's okay here.
Okay. Pratikash, can you confirm if you're all able to see my first slide?
Yes, we can all see it.
Okay. Okay, I think we'll get started. So again, welcoming everybody to this workshop. Uh, I hope you're all able to see the next slide, which has the picture of our campus.
Yes.
If one of you can confirm.
Yeah, it can be seen.
Yes.
Okay, great. So actually, we were supposed to have this workshop physically in our beautiful campus here in Bangalore, in IISc. But because of the COVID situation, we are all forced to meet online. And so just to give you a little bit of an idea about
It's difficult. It cannot be heard. There's no sound.
Audible.
yeah, are you able to you're able to hear me now, Pratikash, on the in the Teams?
Yes, I can hear you.
Yes.
I can hear you now.
Okay, you're all able to hear me? Okay, great. Okay, so let me do one thing. Let me just share my screen again and just get started all over again. So yeah, I hope you're all able to hear me and see me now. Have the picture of our campus.
Yes, we are able to see.
Oh, fantastic. Okay, great. So as I was saying, our institute is about 112 years old. We are a small university, fairly well ranked in the world. Of course, we are considered a small university. Just a little bit about IISc. I'm on the slide which talks about IISc. This is, as I said, it's a small university, but it's one of the leading institutions in India in the area of science and engineering primarily. IISc has laid a lot of emphasis on fundamental investigations and also has worked on practical problems. We have faculty is around 500, and we are sort of let me just get my pointer here. Okay, so we are across 42 departments, and student population is around 4,200, which is why we are categorized as a small university. And we have been very actively collaborating with a lot of industries, both in India and abroad, over the last several years in very strategic and frontier areas. And most recently, the government of India has established, through DST, Department of Science and Technology, has established a National Center for Clean Coal Research and Development at IISc. At any point of time, if you're unable to hear me or see the slides, please unmute and let me know. Okay, I'll continue. I'm assuming I'm being heard and the slides are being seen. So, of course, a quick background for this workshop.
See the slide. You're not able
Yeah,
to see
I'm on the
slide.
slide which says background and motivation.
No, it's blank.
Yes, you're on that slide.
Okay.
Yes,
Yeah, I
I
think
can
some
see.
of you may have, those of you with slightly lower, slower internet access may see the slides coming a little later. So kindly, I think that will be an issue, but yeah, I'll try to spend enough time on each slide so all of you are able to sort of stay with me in this presentation. So I think this slide is sort of not really required for this audience because it's talking about the background for this workshop. Most of you are connected with coal or clean coal technology somewhat, and I think are involved in some level of research and development on clean coal. Yeah, basically the motivation is very clear. In India, we still depend a lot on coal for our energy, and for us, because of the global warming and other climate change concerns, research on clean coal technologies and carbon capture, utilization, storage are very, very important. And the other big challenge for us is our Indian coal is typically associated with very high ash content. So which is why we need, to really look at these technologies. And to add to all of this, India has committed under the Paris Agreement to cut down the greenhouse gas emissions by a significant percentage by 2030. So this, of course, will also require us to cut down dependence on coal to about 40% from our over 70% that we are right now. This is, of course, by 2030. So this requires us to look at clean coal technologies, biomass co-firing, carbon capture, and so on. Again, the next slide on oxy-fuel combustion and CFBC is again not really required here. Many of you are already familiar with this. Of course, oxy-fuel combustion is a very promising technology for CO2 capture because the exhaust is rich in CO2. It typically leads to a smaller unit size and cost. And of course, we still need to use some of the we need to recycle the flue gas to reduce the temperatures. Otherwise, that can create other issues. And CFBC, which is sort of the focus of this workshop, has several advantages. A few of those are listed here. One, of course, is that it can operate with a wide variety of low-grade fuels, particularly high ash Indian coal. It can be co-fired with biomass and municipal solid waste. And of course, there is in situ sulfur removal. And it's generally associated with the low NOx because of the lower temperatures. And of course, you can have 100% wet flue gas recycling. Of course, in India, the majority of the boilers are still, based on pulverized coal technology, but there is a significant percentage of boilers now with CFBC. So I'm on the next slide, which talks about activities at IISc. Here we have two major projects. The first one is funded by Ministry of Human Resource Development, and this particular project, which is known as SPARK, SPARK is a scheme to promote international collaboration. So the MHRD has funded a project between IISc and Chalmers University, Sweden. In fact, this project is going to come to an end in a few months, and this support has facilitated visits of faculty and students, lecture series, and in fact this particular workshop that we are having. So these were the activities under the SPARK project. Now we have a separate ongoing project funded by the Department of Science and Technology, Government of India, on oxy combustion for CFBC. And here we are involved in quite a few activities. I'll talk about this very, very briefly over the next 10 minutes. On right from single particle coal combustion studies all the way to a pilot plant. Now, the MHRD sponsored Chalmers project, the IISc Chalmers project, as I said, involved visits by IISc and Chalmers faculty. Unfortunately, the Chalmers faculty could not visit because of the COVID, but we did have a chance to visit, and our PhD student was also able to visit there. This project also required us to conduct a lecture series, which was recently concluded and very well attended. And the third is the academia industry joint workshop, which we are currently having right now. So these are the activities under the MHRD sponsored SPARK project. And of course, in this project, the collaborating team, of course, from here, it's myself and Professor Pratikash Panda and Professor Bo Lechner and David Polaris from Chalmers University, Sweden, who are, of course, experts on the CFBC technology. They've had many years of research and development and even demonstration units on these technologies. So we are getting a lot of support and help from Chalmers in all our activities that we are doing at IISc, and including this workshop. In fact, this is just a flyer of the lecture series that was recently concluded. It went from 25th January to 4th February, a very successful lecture series on Introduction to Circulating Fluidized Bed Combustion, again conducted by Professor Lechner and Professor Polaris. And the contents of this course are sort of briefly shown here. So a very in-depth course covering the basics of circulating fluidized bed combustors, and right from the hydrodynamics to heat and mass transfer aspects to combustion and modeling and measurements, and finally the emissions. So it was a very comprehensive course. Many of or several of you in this workshop have probably attended and benefited from this particular lecture series. Of course, this slide brings me to this current workshop that we are organizing, and this is of course just, you already have the schedule with you, but I've just put up this slide just to let all of you know that we have a very impressive list of speakers from India and across the world, and a balanced perspective from academia and industry on what can be done in India in the future on CFBC. I come to the second part of my presentation, which talks about the work that Department of Science and Technology is funding at IISc. And as I said, this is on oxy-fuel CFBC. And there are two aspects of this. One is coal characterization, and the second is coal combustion, both at the particle level and at bench scale, and finally a pilot plant. I'm just going to spend 2-3 minutes on this, just to give you an overview of the kind of activities that basically we are conducting at IISc. So this is a schematic of an experimental setup that I just wanted to show you, where we do single coal particle combustion studies. So we create a flame of hydrogen and using diluents like CO2 to create an oxy combustion environment. So the idea is to create an oxy combustion environment and subject a single coal particle to this environment and then study the combustion of this particle. So this is more of a fundamental study. It gives us, of course, various information about the coal particle depending on its size and environment. We can get the various burnout times. And we can also do some more sophisticated studies using optical imaging. So we can try to also measure the temperature of the particle as it burns in this kind of an oxy combustion environment. So these kind of studies are being done. Of course, I'll skip some of these details. This particular slide shows you the single particle combustion. So these are some images of a single coal particle being subjected to this combusting environment. You can look at the way you can see the different stages from the particle heating to the volatile combustion to finally char combustion and finally the ash residue. So we can measure the time burnout times or the time that the particle spends in each of these stages. And we can also do measurements, direct temperature measurements and imaging measurements and so on. We are also trying to come up with a bench scale CFBC, and this is going to be unique because this will be an optically accessible CFBC bench scale setup. This is essentially to recreate and understand several physical phenomena occurring in an actual CFBC, of course at a much smaller physical scale. We believe that this can be an ideal bridge between the single particle studies and the pilot plant that we hope to set up at IISc. Of course, it will allow us to reproduce conditions observed in various regions of a CFBC, such as the sand bed, the splash zone and the riser. The optical axis will allow us to measure the temperature using pyrometry. We plan to incorporate a furnace type radiative heater to heat up the sand bed to essentially create real CFBC conditions. And in some sense, the transient measurement of emissions will also be possible. And we have received a lot of support from Chalmers University, thanks to Professor Lechner and Professor Polaris in the design of this particular bench scale setup. So this just gives you a schematic of this particular setup that will be installed at IISc to do all these fundamental measurements. Again, in the interest of time, I'm going to skip all this. I'll come to the last slide of my presentation, essentially, which talks about the pilot plant that we want to set up. Now, I mentioned to you briefly that this is one of the goals in the DST sponsored project. So we want to design and develop or demonstrate a 100 kilowatt pilot plant, which can operate in an oxy-fuel mode to demonstrate clean coal combustion with carbon capture and utilization. We want to demonstrate biomass and municipal solid waste. The idea of this pilot plant is to, that this facility will be available for industry for either training purposes and also for research organizations like ours to conduct benchmark experiments. More importantly, we want this facility to be to showcase CFBC and advanced technologies, and we would really like the industry partners to come forward and support IISc to develop and get this pilot plant going. So we'll talk more about this maybe towards the end of the workshop. So with this, I come to the end of my presentation. So just to summarize, I just wanted to give you a background of this workshop. So this is part of the MHRD sponsored SPARK project, which enables collaboration between IISc and Chalmers. But I also gave you an idea of the work that's being done at IISc as part of another DST supported project. So with this, I close my initial welcoming remarks to this workshop. And I would now like to introduce to you the inaugural speaker, because in a few minutes we will be having our inaugural lecture for this workshop. So I hope all of you can see this slide. Today we are very fortunate to have a very eminent person inaugurate this workshop. So Dr. V.K. Saraswat, who's currently a member of the Niti Aayog Government of India, has kindly consented to inaugurate this workshop. So I've just shown a very brief bio of Dr. Saraswat, who's one of the most gifted scientists and researchers in our country, spanning both applied and basic sciences. And apart from being a scientist from the defense sector, he's been a innovator, technologist, and a visionary. In fact, in his career, from a scientist in the defense sector to the scientific advisor and even to the defense minister, and eventually as Secretary at Department of Defense, and currently, of course, member Niti Aayog, he has been credited with the development of several liquid propulsion rocket engines. He's been the principal architect of the ballistic missile defense program, which included very major technology breakthroughs. In fact, with this activity, India has joined the select nations that have the capability to have a ballistic missile defense program. Of course, under his leadership, DRDO has also developed several technologies for societal benefit. A few of them are listed here, such as the solar-powered modular green shelters, biodigesters, the HAR programs, explosive detection kit, and diagnostic kits for several of the diseases. Till recently, Dr. Saraswat was the DE Homi Bhabha chair, and in fact, energy has been a very favorite topic for Dr. Saraswat. He's initiated development of technologies for energy security in the biomass area, solid waste management, fuel cells, CSP, photovoltaic cells, clean coal technologies, and he's also been a champion of the methanol program in the country. And he's been very actively working with industrial and academic institutions in also bringing in new dimensions to the aerospace manufacturing sector. He's been a member of several professional bodies, but more importantly, some of the important awards that he has been conferred with. Of course, the Padma Bhushan by the Government of India in 2013, the Padma Shri in 1998, the Vikram Sarabhai Memorial Award from the Indian Science Congress, the Lifetime Achievement Award by the Ramakrishna Vivekananda International Foundation, New Delhi, Professor Jai Krishna Memorial Award by the INAE, Dr. Nayudamma Memorial Gold Medal for the year 2011 by the AP Science Congress, Jawaharlal Nehru Science and Technology Award by the Government of Madhya Pradesh, the FICCI Annual Award, the Aryabhatta Award from the Astronautical Society of India, and the National Aeronautical Prize in 1998. So, in fact, there are several more accomplishments of Dr. Saraswat, but I have tried to just convey the most important ones here so that the audience gets an idea of the kind of experience and expertise that he has. And currently he's really championing many of the scientific initiatives in our country, particularly related to energy. So with this introduction, I would like to invite Dr. Saraswat to give his comments and his suggestions on a roadmap for India in the area of CFBC technologies. And yeah, I would like to now, I'll unshare my screen and I would request Dr. Saraswat to give his inaugural lecture.
Good afternoon. I hope I'm audible and
yes, sir, you're audible.
Communication with you. I'm going to make a small presentation on the subject what we are discussing today, which is on workshop on clean coal technologies for India, and you are also talking about circulating fluid as bad combustion, gasification for carbon capture and biomass co-firing. My interest in this subject has been very old. When I was scientific advisor to the defense minister, that was the time I started looking at multi-feed combustion and gasification systems for energy, although it was not directly related to the defense activities. But I was of the opinion that we should certainly create energy for the armed forces using this process in some way in a distributed manner, because they have huge military farms where large number of agricultural activities are taken up, and you have huge biomass available. So from that time onwards, and through the IIT Hyderabad, as you mentioned, we have been into this activity. When I came to Niti Aayog, I developed my interest in methanol economy. There again, the basic production methods for manufacturing of methanol, were identified, and one of them was biomass to methanol, coal to methanol, and things like that. So I'm going to talk to you about some of these aspects of clean coal technologies, particularly the point of circulating fluidized bed, because India today has launched a major program on coal gasification and production of methanol and other chemicals from coal as a resource. And I don't know how many of you have kept track of the announcements which have been made by the Department of Coal, and particularly the Secretary Coal, where he has said that about 4 to 5 centers will be developed for coal gasification. And there, by and large, the processes that are being followed are either the undrained bed gasification or the or the circulating crude oil bed gasification. So let us just start with the energy scenario. I'll share my presentation. I hope it goes there. It's not opening here. Yeah, can you see my screen, please?
Not yet, sir. You can see your video, but not the screen yet. Yes, sir, we can see your screen now. Yes.
Yeah, thank you. So I'm going to talk to you about future prospects of CFBC for carbon capture and biomass co-firing. That is what we want to see. But I want to start with a clear picture of what the coal resources in India, because coal is one of the major feedstock for this particular activity of gasification and circulating fluid oil bed combustion. You can see from this particular graph that we have the production of coal during 2019-20 was about 729 million tons. 24% of course still of the coal requirement we are importing for various reasons, particularly from the economy point of view, but otherwise we are self-sufficient. We have proven results of almost 42%, we have indicated results of about 48%, and 10% are inferred. So 326 billion tons of coal resources is estimated by the Geological Survey of India at a depth of 1200 meters in the year 2019. That means we have rich resource as far as the coal is concerned.
So we can still see only your first slide, sir. Maybe you can just share your screen and go to the PowerPoint, slideshow mode. I think we're still on your first slide only.
But here it is changing. I'm able to change. Can you see that now?
We're still seeing only your first slide.
Slides are not changing. Then I'll have to go back to the most probably slideshow on the. Can you see my first slide?
Yes, sir. It's not in the slideshow though. It is still in the regular mode. It's not in the slideshow mode for some reason.
Could you expand the figure?
Now?
I think it's still in that mode only, sir, not in the slideshow mode. I think when you share, maybe you can share the PowerPoint file rather than the screen, maybe. When you share, I think
PowerPoint file. Let us see. PowerPoint.
Yeah, when you share screen, you click on the PowerPoint file. When you say share screen, you get options. You can click on the PowerPoint file, and that will then ensure that only the PowerPoint file is shared, is shown on the screen.
Can you see the full screen now?
We are seeing the slides. It's not in the slideshow mode, but we are seeing the first slide only, I think.
Now you see if it is changing.
Could you see the second slide? You have to press the sign on the bottom to expand the figure.
Now here it is changing. My PC is changing. But at your end, it is not changing. I do not know why. Here, all the slides are changing.
Oh, it's not changing here.
At your end, it is not changing means
It's
what?
not. Or you can email it to me, sir. I can share it.
Stop sharing. Well, first stop sharing and then try again. Email to him.
You can email it to me. I can share, or
We are emailing to you. That's a problem. Did it make any difference?
No, sir, still the same.
Only first slide.
First slide, that too not in the slideshow. There is a resume slideshow. Can you press that? It is seen on your screen.
Are you seeing now changing in this mode?
And now we'll move to the second slide.
Yeah, in this mode it is changing, but when I do in the slideshow mode, the slides are not changing at your end.
Okay,
you can continue in this mode, sir. You can just increase the zoom a little bit, maybe. You can increase the zoom a little bit, and you can continue in this mode, no problem. You can increase the zoom a little bit. On the bottom you have the zoom. You can increase the zoom a little bit and continue in this mode. Yeah, this is perfect.
Is it at least legible to some extent?
Yes, we can see very clearly now, sir. You can go on this mode.
So we are talking. I'm sorry. We can go back to my previous slide where I talked about the coal resources, and I mentioned that India has 326 billion tons of the coal resources till as found out till 2019, and we are importing 24% of the coal, and we still have about Indian production of coal during 2019-20 was about 729 million tons. So we have huge reserve. India has largely and rapidly growing energy needs also, because we have a situation where we have 77th largest economy, and we have third largest energy consumer, and we are the fast growing economy today. And population and the economic growth will drive the demand for energy. Our energy mix today still is about coal is about 44%, oil is 25%. And biofuels and waste is about 22%, natural gas 5%, renewables 2%, and nuclear 1%. So this is the kind of scenario we have. Nearly 97% of our households, in fact, this figure has now changed. It's about 99.9 is the kind of electrification that has taken place. In 2027, because we are also trying out a lot of exercises as far as the energy mix is concerned to meet the kind of goals we are setting for carbon dioxide reduction, greenhouse gas reduction, and so on. So there's a huge renewable penetration which is taking place. That robust energy mix which is going to emerge in 26-27 is getting around 43% of its installed power capacity will be from clean energy sources. And we expect that from the installed capacity of about 372 gigawatts today, we will be inching to close to 640 gigawatts by about 2027. Among that, I think, of course, the maximum growth is going to take place in the renewables from 88 gigawatts to as high as 275 gigawatts. But coal will still be significant, because today we are about 205. It will go to about 248 gigawatts. So you can see that the technology related to coal, particularly coal combustion, coal gasification, clean coal technologies will certainly be the driving factor for many, many years to come. Why coal? As I mentioned to you, because it is readily available worldwide, strong international trade, relative low cost, and lower price volatility, not like the crude oils which keep fluctuating up, not down, mostly up, and has lifted population out of the poverty in the many cities, very suitable for grid-based power generation. in India, we are saying that the share of global energy demand would rise to about 9% by 2035. And share in the primary energy consumption will be, as we have seen here, compared to the other nations, Brazil is 2%, India 9%, US about 13%. Among this, the share of coal-fired power generation will fall, but still remain quite large, as I had shown in the earlier slide also. Like today, 72%, and it will come down to about 42% by 2040. This is the kind of prediction which we have made, and this is what we are making use for our planning processes. The energy, if you look at the primary consumption of energy, primary energy consumption, you will find that we will go to about 48% will be coal in the about 2040. This is the primary consumption, dominated of course by coal again in this case. Our future power plants, many of you are instrumental in advising us on this, and you know that today India is working in a big way on improving the plant efficiency, and in that direction we switch over from subcritical to supercritical. Then we are switching over to ultra supercritical, and there's a major R&D program which has been taken up for advanced ultra supercritical, thereby increasing the efficiencies beyond 40%. So that is also going to happen, and modular unit sizes of approximately 50 to 350 megawatts. Nearly we are planning for near zero emissions because there is a strong push for carbon dioxide sequestration and storage and utilization. So that's going to reduce all kinds of emissions what we have today from the thermal power plants. It is possible to ramp high ramp rates, minimizing water consumption, and also making sure that we have better part load operation capabilities and things like that. Reduce design, construction and commissioning schedules, enhance maintenance free features, and integrating with coal upgrading. This is what are the traits of the future systems. We have a major thing as far as the coal is concerned. We call it reimagining the coal. Products from coal, coal resources, ash and byproducts. So coal and coke and pitch and tar, these are the major inputs as far as this sector is concerned, which has got three major elements. One is manufacturing and processing plant. Another one is of course the power plants what we are talking of, and third one is coal mining and resources. So manufacturing and processing plants certainly give you variety of outputs in terms of concrete and coatings, energy, carbon nanomaterials, structural materials and so on. When you talk of power plants, you get steam and power as the output, and of course whatever ash is being produced, that goes into again manufacturing sector for manufacturing the bricks and gravel and things like that. The coal mining, of course, and gasification certainly is a process, which is the major process where we are looking for now as part of the hydrogen economy, and also the production of coal to chemicals like methanol and fuels like ethanol and methanol and ammonia and chemicals and power. So these are the things which are major outputs which we are planning for. So coal mining resources, shale, clay and mine drainage, sludge, leachate, and one major push we are giving today is to get more and more rare earths and critical minerals and things like that from this particular resource. So it's economically a most relevant thing today, and this is going to make a difference as part of our clean coal and clean energy technology programs are concerned. There is a major R&D push on the CCUS, carbon capture and utilization and storage. So in that utilization portion is very, very relevant. Storage of course is important, but utilization is more important. And one of them is of course the extended oil recoveries, the direct utilization of carbon dioxide in terms of welding, dry ice and things like that. And the carbon recycling, which is again a major area where we are looking at production of chemicals and fuels and the minerals and others. These are the a few things which are among the chemicals are very important today, and this was witnessed during the pandemic, that our key source materials for most of our medicines today, including what we call as the active pharmaceutical ingredients, API, our supply chain is quite dependent on the foreign inputs. So there has been a major push by the Department of Pharmaceuticals today to convert coal into different KSMs and KSMs into APIs and finally for the medicines. So there's a huge push in that direction. Also, there's a push on commodity chemicals like olefins and so on. Fuels, of course, my major push is on methanol, where we would like to use it for a variety of applications. And minerals like concrete products, concrete structures, carbonates, and things like that. So advanced coal provide the best path for achieving environmental goals. You know that India is committed as per the COP21 for reducing by 15% to 30% the carbon dioxide or the greenhouse gas emissions to maintain the kind of temperature growth or the global warming we were talking of. So high temperature and pressure drive efficiency in advanced supercritical coal plants. I mentioned to you about the advanced supercritical which we are doing today, where we are reaching the limits of about 700 degrees Celsius and so on. And we are also operating boilers at about 300 bars. High efficiency advanced plants produce more electricity per ton of coal. And every 1% efficiency gain reduces lifetime emissions by about 2,000 tons of nitrogen oxide and sulfur dioxide, and 2.5 million tons of CO2. So that is the importance we are attaching to as far controlling as far as the greenhouse gas emissions and pollution is concerned. So the following clean coal technologies, among them, of course, is the circulating fluid as bad combustion, is the near zero emissions, ensuring that the particulate criteria pollutants, particularly the SOx, NOx, and the particulate matter and greenhouse gas emissions, they are controlled. Emerging technologies are, of course, IGCC. While India paid attention to IGCC long back, I remember the initial first step was taken up by PHEL to set up the IGC plant, but for reasons of economy, I think it was shelved. And of course, we have a habit of seeing what is happening in America, and we found that America has reduced their push on IGCC. So we also tried to copy them, and as a result, that particular exercise was abandoned. But I think after this methanol program, when I started, we are giving a major push on integrated gasification systems. Advanced ultra supercritical combustion, this is another program which is on oxy-fuel combustion is part of this. So carbon capture and storage, in this the major push is now conversion of carbon dioxide from various thermal power plants and steel plants and refineries into methanol. So CO2 to methanol is one of the major initiatives which the government of India is taking for ensuring that whatever bulk CO2 producer organizations are there, like cement production, steel production, these refineries and all that, we are able to take out the CO2 from flue gases and then convert them into chemicals. So the processes of using the coal combustion and gasification, and in that I have highlighted CFBC, and which is one of the major. It could be atmospheric or it could be pressurized system, other than of course IGCC as part of the gasification program. Sorry. So need of the hour is developing efficiency technology to minimize impact on CO2 emissions. If you see the today's scenario, when we were using the brown coal, which was pulverized, we had tons of carbon dioxide per megawatt hour of electricity production in the region of 1.1 to 1.3 or 1.4. Today, when we are using black coal pyrolyzed fuel, this has come down to about 1. And as you proceed further, it is going to come down less than 1, about 0.7, 0.5 when you go for integrated gasification combined cycle. And keep on improving the efficiency of thermal efficiency of the systems. This is where we are from 30% as you move to about 50%, close to 50%. You are in the region of 0.5, 0.6 to 0.7 tons of carbon dioxide per megawatt hour. So that is our direction in which we would like to start moving. So clean coal technologies are a key step towards near zero emissions from coal. And technologies are reducing coal consumption, reducing non-greenhouse gas emissions, and carbon capture and storage. And these are all at various levels, like reducing coal consumption is part of the thermal efficiency improvement, as we discussed. reducing GHS with pollutants to be reduced. Of course, measures have been taken like flue gas desulfurization, filtering cyclones and all that, and then mercury also now, and carbon dioxide storage. While many countries were talking of taking carbon dioxide, liquefying it, and putting it into the caverns and so on, I think India will do better to capture it and do a storage and utilization for production of chemicals. That is the kind of approach we should take. That will be more economical, and it will also be like the real circular economy. So clean coal technologies during various stages of coal life cycle are preparation of coal, coal beneficiation, coal blending, coal liquefaction, underground coal gasification. These are some of the preparation part. India has not given much attention as on today to underground coal gasification, while there is a lot of analysis being done. But I think technologically we still have a long way to go. Whereas overground or the surface coal gasification, we are finding that as a much easier path to follow. But certainly, since this is an international platform, I'll be welcoming any country, any organization who is interested in working with us on the underground coal gasification, because that is one area where we have a major stake at the moment. Burning, of course, today's combustion pathway and the gasification pathway, where we would like to reduce the carbon dioxide emissions as much as possible, and carbon capture and storage and combined cycles. Sorry. So clean coal technologies, as I mentioned to you, we have 42% current efficiencies to going to about advanced ultra supercritical with CCS and oxy-fuel combustion to the region of more than 50%. Gasification similarly. And our answer to that is the fluidized bed. While India has a couple of, I would say, gasification plants where fixed bed has been done, and now there's another project is being done at Talcher, where we are going to go for an entrained bed kind of an approach. But our experimental trials are all on the circulating fluidized bed systems, because India has got one disadvantage in terms of the quality of coal, because we have high ash content coal, and that is better handled with the fluidized bed system compared to the other systems. And of course, you have clean coal technology options where you can do co-firing of the biomass, which gives you great advantage as far as the fluidized bed systems are concerned. To make a comparison of these combustion and gasifier types, there are 4 parameters on which I have looked at them. One is, of course, feedstock tolerance. Another one is the syngas quality, what it produces. What is the status of the technology? Another is what is the potential for scale up, and what is the cost in setting up a plant. And so based on this, we have done the ranking, and we find that of course, the entrained bed has got the rank number 1. But in terms of the handling of the ash, and also taking into account the co-firing of the biomass, I think the circulating fluidized bed gasifier and combustion unit is the best suited. So that ranks number 2 as far as our scheme of things is concerned. And if you compare them on the basis of ash limit, on the basis of temperature, on the basis of fines handling capability and the capacity, and again on the development and what is the tars and oils form, again you will find that the best thing that emerges is the fluidized bed and entrained bed flow. So this is one thing which is very clear, but unfortunately we have one plant at I think Odisha, which was run in Jindals, where they have gone for a fixed bed using the technology from South Africa. Now, a typical conceptual image of a CFB boiler is given here, where you can see the distinct advantages. You can see the biomass, which is less than 50 millimeter or something of that size. Then you get coal, which is about 10 millimeters in that size. Then you, of course, feed in limestone for controlling the other sulfur and things like that. You got about 1 millimeter. And there are distinct advantages of this particular. You can see how the whole process of recirculation takes place in this from the two chambers. And you have fuel flexibility. Circulating solids provide high thermal inertia for stable combustion over a wide range of fuels. Then very low NOx levels, where excellent mixing in cyclones minimize ammonia slip, and stringent NOx limits can be achieved with SCR catalyst. Then we have sulfur captured in furnace. Effective and economical sulfur capture in furnace using limestone. Calcium-rich ash can be reactivated for further SOx reduction, recycled or inactivated. And you can get long burning time, low ash carbon content, low carbon monoxide. So this is another one. And it has been observed and reported that there is a low maintenance cost, no ash slagging, which minimizes furnace corrosion and fouling. Circulating solids keep furnace surfaces clean and minimize the deposit buildup. So there is a distinct advantage and the kind of thing which you can achieve as far as the CFB boilers are concerned. If you take a gasifier, in this the fluidized bed gasifiers gave the reactors where solid particles material is suspended in moving liquid or gaseous fluid. Some can contain even nickel particles to promote decomposition of hydrocarbons to carbon monoxide and hydrogen. And CFB gasifiers can handle high ash content fuels. They are well suited for continuous operation and scalable to a wide range of sizes, allowing for large-scale industrial plants. In fact, we have been doing some studies and we found that scaling up, although people say that there is a problem, but I think we have found that even large sizes of single plants can be set up. Otherwise, the capital cost can be reduced by choosing the optimum size and then modularizing it. The CFB gasifiers are also somewhat cheaper to construct than the BFB bubbling bed gasifiers for corresponding capacity. And advantages: feedstock flexibility resulting from easy control of temperature, which can be kept below the melting or fusion point of the ash, and in the case of biomass, it is the husk, and the ability to deal with fluffy and fine grain materials like sawdust without the need for pre-processing. Otherwise, you have to do the RFDE and things like that. We may have some problems with leading instability of the bed, and fly ash sintering in the gas channels can occur with some biomass fuels. And we need a minimum loading of biomass. It should be not less than 70%. So these are some of the operating parameters which have been worked out for the different combinations of combustors as well as the gasifiers. Some of other features of the fluidized bed combustion are different density. You can have different sizes. You can have high moisture content. You can have circulating fluidized bed with different density can prevent deposit of waste in the bed. And new CFBI technology combined with fuel inner and outer cycle ensures combustion stability. Then low heat value, difficult to be burnt out, low combustion efficiency. These are also taken care of by circulating ratio of close to 10 to 20, low rate of slag less than 2%, low rate of stove grade incinerator slag is about 5%. So you have distinct features which make CFB as the preferred option. And there are of course boilers which are great furnace boilers and CFB. There's a comparison given here. If you see the steam pressure, I'm talking of conventional boilers, but we know that now we are having boilers like 300 bars also. So steam pressure about 4 bars, then medium pressure in the CFB is about 3.8 bars. Steam temperature 400, it's about 450. Exhaust gas temperature 190, 150. Like that, you have different advantages, different features. Primary air temperature particularly high. The primary air temperature of the latest type furnace can reach above 350 to 250 degrees Celsius. It makes use of the waste heat of the tail flue gas to heat the air. So that's the advantage we have. Now, what are the other fuels which you can take? you see the burning difficulty is shown with in the increasing order, and the heating value has been taken. The easiest to burn, of course, are the coals like the anthracite, bituminous, brown coal, peat, bark, and others. Whereas as you go further down, you find that PVC and things like that become very difficult to burn. They have burning difficulty. Paper and wood have slightly, the chicken litter as well. So there is a distinct order in which the choices can be made, and you can get the right kind of biomass which will be able to be used along with the coal in the system. What are the environmental benefits? Inherent impurities like sulfur compounds, tar, nitrogen compound can easily be removed in the case of CFB. Low levels of nitrogen-based compounds have been constantly observed in all plant-scale CFB systems. A high carbon conversion rate per unit cross-sectional area is one of the major advantages of CFB. If co-firing of biomass with low-grade coal like peat and lignite is done, then the net carbon emissions can be greatly reduced. In fact, this is one program which we are planning in Chennai, Lignite Corporation of India, where we are trying to go for a circulating fluidized bed gasifier and a combustor, where we will mix the biomass along with that to achieve this kind of a performance. And it is the first of its kind which we are planning in Chennai. Ultra supercritical pressurized CFB system with pollutants and carbon capture technology can further increase the overall efficiency and it make it very, very friendly. What are the challenges and hindrances in implementing this technology? There are some challenges, and prominent among them are CFB systems are generally of very large capacity, that is 10 to several hundreds of megawatt capacity, and involve a lot of initial capital investment. This is where we have to do a lot of ingenuity in R&D to keep the capex as low as possible. This technology is relatively new to the manufacturer, so it will be difficult on their part to manufacture it on mass scale. Yes, this factor is a very important factor, because when in India we were trying to make a choice for the culture plant, there was a choice available for going for CFB. But because of the past experience of the engineering companies and also very little experience in India, the choice boiled down to entering back. But I personally believe that for an ash content, in the culture plant, we have been able to mix the 40% ash content coal with pet coke, and thereby reducing the average ash content and then making it burn. But if you have to do it with 40% ash content and pure coal, then it is going to be a difficult option if you go only for entering back. This is my observation. Of course, the teams can agree, can discuss and come to their own conclusions. Agricultural lands in the country are of defragmented nature, which restrict the use of high mechanization, resulting in reduced efficiency and increased procurement cost of biomass and coal feed. This is another major issue. Whenever we go for a biomass kind of a product or an industry, the cost of biomass keeps on increasing, thereby making the system more unviable. Biomass price on constant rise after commissioning of the new power project. This is the observation. It is common human mentality that waste is equivalent to ash, so they are least bothered about its utilization. This is now global. What is the global market? Global market value in 2018 for the circulating fluidized bed boiler is about 38 billion. Supercritical boilers are steam generators which operate at 3200 psi and temperatures ranging from 538 to 565. I am now talking of advanced ultra supercritical boilers where the temperatures would be about 700 and the pressures would be about 300 bars. The demand for petrochemical products has witnessed a significant growth over the past decade owing to the declining crude oil prices. This is what, and global market in 2025, that's not far off, is going to be about 50 billion. So that is a major investment which can be done for those who are interested in really working on the circulating fluidized systems. For India, it is very clear because we have fuel flexibility and inherently low emissions requirement without the need for expensive emission control systems. So this certainly helps. The combustion temperature in CFB boiler 800 to 900 degrees Celsius is significantly lower than a pulverized fuel boiler where you reach 1300 to 1500. Reduced NOx production while limestone injected into CFB furnace captures most of the sulfur in the coal, achieving about 95% reduction in sulfur dioxide emissions. It can bring high value to India with its large reserves of low quality coals because we have high ash content and I think for India it is the best technology. CFB technology has been proven at large scale to economically, cleanly and reliably converted these low rank fuels into power and steam, lowering the country's energy cost and improving its energy security. The fuel and emission flexibility offered by CFD translates into more value for power project developer in terms of capex and opex. So we have that advantage. This is a typical. This is one of the diagrams of photographs of the plant which was set up in BHEL way back. It worked for about 20,000 hours, but I think today it is not in operational condition where we have gone for circulating fluidized bed systems. There is now we have carried out research where the advanced pressurized fluidized bed gasification unit is operational now. They are working about 1.2 tons per day kind of a capacity, and the plant is just made operational for production of methanol using the circulating fluidized bed. You have the rising demand of low emission systems driving the biomass technology adoption. So ongoing transition toward the adoption of clean energy fuel sources to generate electricity has really brought in the penetration of sustainable technology multiplier industries. And we have boilers not only limit the discharge of harmful emissions content, but also subdue the reliance on non-renewable energy systems. So there is another area. Co-firing of biomass is a major advantage as far as CFB is concerned. It reduces the emissions of greenhouse gases. Co-firing in coal plants will strongly increase biomass use. Lowest capital cost option for increasing the use of biomass to produce electricity, and co-firing biomass and coal takes advantage of the high efficiencies obtained in large coal-fired power plants and improve combustion due to the biomass higher volatility content. So that is the advantage. You can see CO2 emissions for a 300 megawatt equivalent plant with CFB and biomass co-firing. We have different kind of units here, like the PC drum. PC drum is a pulverized coal drum, and PC ultra supercritical, then CFB drum, then CFB USC and CFB USC 40% biomass. Biomass keeps on increasing, and you can see a pure coal system. We get almost about 912 grams of carbon dioxide per kilowatt hour. Whereas if you go to 40% biomass, you can get as low as 438. And the red line shows about the limit which has been set about 475 grams CO2 per kilowatt hour. So there is a distinct advantage if we are going to do co-firing of the biomass along with the circulating fluidized bed coal combustion. There are technical barriers. For example, yes, there is a fuel flexibility in co-firing in terms of quality and quantity, but it has to be chosen with a lot of care. Complete combustion and well mixing boiler should be achieved, and fouling and corrosion of the boiler like alkalis and chlorine still have to be solved. Ash utilization, unburnt carbon and contamination, and negative impact on flue gas cleaning. So these are some of the barriers which have to be handled. And there are, of course, non-technical barriers, as I mentioned to you, that the prices keep going up as the biomass keeps coming into operation. There are certain legislative aspects of utilization of fly ash and cement determining green share emission legislation, and public perception of co-firing of biomass and the waste. That is another one which has to be removed. This is the production plant which is being set up now for gasification from methanol production, where you can methanol gas synthesis and then syngas scrubbing and then production of the methanol. This is another BHEL capability where we are setting up about 0.25 TPD plant with high ash content coal. And by the way, we are able to demonstrate in this particular plant very clear, very good gasification of high ash content coal without reducing the ash content by any blending or mixing. And the performance has been very stable in this particular case. So this plant has to be now scaled up for production of methanol. A possible roadmap for the introduction of the new technologies involving the utilization of coal for energy. 2020, we have improvement of the existing plants. Then, of course, CVFC co-firing we do. Then CVFC systems. Then ultra supercritical boilers, we have to go, not only supercritical, we have to now go in the country in a commercial scale, the ultra supercritical boilers. Then combustion and gasification and CO2 capture. NCPC has recently come up with a plan for setting up CO2 capture and conversion into hydrogen, that kind of CO2 and hydrogen into methanol. So that's an excellent project, and any national and international companies, if they are interested, it's a great initiative, and that will also bring in a lot of circular economy in our system. And ultimately, we should be able to use oxy-fuel combustion and CO2 capture, which will give you the highest efficiency and the least emissions. And by the time we reach 2050, I think this is a building block for achieving the hydrogen economy, because coal-based and the renewable hydrogen, this is going to be a major source for producing methanol, and then we can have methanol as a storage for hydrogen, and that will usher in the hydrogen economy in the country. These are some of the advantages which I have already discussed. I won't repeat them. But coal gasification as a precursor of the hydrogen economy. You can see here that average cost of the solar PV, that the levelized cost of hydrogen US dollar per kg is in the region of about $7, 85 US dollars per megawatt hour for that matter. And as you come down, the best case is the wind, 25 US dollars per megawatt hours with low cost of electrolyzer and about 200 US dollars per kilowatt. So these are the way the advanced natural gas reforming cost would increase by 13%, while for hydrogen from coal gasification, cost would decrease by 11% by 2050. That is a kind of scenario which has been seen. And green hydrogen or even the blue hydrogen, these are the things which are going to stay with coal as one of the major source for its production. So coal gasification and combustion becomes the most important thing as far as we are concerned. So what future could be expected? What are the R&D needs? I'm at a platform which is international platform with Indian Institute of Science, one of our premier institutions taking the initiative in this. So I will not shy away from discussing the R&D requirements. We need improved component design, such as internal recirculation systems, leading to more compact systems. Broadened range of fuel flexibility. As I mentioned to you, we are able to do co-firing, but I think we still have to expand the range so that it becomes more stable. Today, the stability becomes an issue if the choice of the biomass is not done very properly. Introduction of supercritical and ultra supercritical steam cycles has to be done, because that is the future. And development of improved materials of construction. And although we are in the region of 900 degrees Celsius, but I think to reduce the capex and also reduce the corrosion problems, I think some other materials also have been thought of. Technology development with 600 megawatt target, because that is where we should look at. Use of CFBC technology as part of the advanced cycles. Increasing solid recirculation in the combustion chamber to allow improvement in the abatement efficiency of SO2 and reducing the sorbent consumption. So ash utilization in markets other than just cement, which is one of the programs which we have taken up. Any ash for that matter, whether it is from the today's plant or tomorrow's plant, the ash utilization of ash for extraction of rare earth materials, and also building value-added products like cement or gravel or bricks or whatever that. I think there's a huge potential and a good market. And finally, the most important aspect for CBFC is reduction in cost and size optimization. So these are some of the R&D areas, and I think this platform should be able to give enough attention and exchange notes in finding out ways and means to mitigate some of these problems and make circulating crude oil bed combustion and gasification as a real thing as far as India's high ash content coal and generation and reaching the hydrogen economy is concerned. Thank you very much. Wish you all the very best.
Thank you so much, Dr. Saraswat, for a very, very comprehensive presentation on the CFBC and the theme of this workshop. In fact, you really have set the stage for all the remaining presentations, because you have brought out the challenges that we foresee in India for scaling up CFBC. So I think this sets the tone for the rest of the talks that come up in this workshop, including both academic and industrial. And in fact, your slide, that one slide which talked about the R&D needs, is something I think that will be debated towards the end in the panel discussion. So thank you again for giving us your valuable time and sharing your thoughts and guiding us on this. Thank you very much.
I'm sorry that I could not show you in full form the slides, but I don't know, even now I don't understand why it didn't happen. But
no problem, sir. We could actually see it well. Once it was zoomed, it looked good. No problem at all.
thank you.
Thank you so much, sir. Thank you.
Okay, all the best. Thank you.
Thank you. I now request my colleague, Professor Pratikash, to handle the rest of the talks from the industry, from the academic and industry speakers. So, Pratikash, can you conduct the next session?
Thank you, Brother Ravi. I once again would like to thank Dr. Saraswat for an insightful presentation on key technological aspects in the aim for coal combustion in the country. So now we have a series of very interesting talks lined up. The first talk of the session would be by Professor Bo Lechner, who is a senior faculty member in the Department of Space, Earth and Environment in the Division of Energy Technology in Chalmers University of Technology, Gothenburg, Sweden. He is also one of our co-PIs in the project. Professor Lechner would be talking about future prospects of CFBC for carbon capture. Professor Lechner himself has several decades of experience in the area of CFBC, and his primary research areas are in the aspects of design of fundamentals and utilization of fluidized bed combustion and gasification of solid fuels, which includes both coal and biomass. And one of the important tasks that he's involved in is to understand utilization of fluidized bed for CO2 reduction. So now I would like to welcome Professor Lechner, and Professor Lechner, you may take the stage now.
Yeah, thank you for your introduction. Do you hear me okay?
Yeah, yes, we can.
And I would like to start saying good afternoon to the Indian participants, and still good morning to the European ones. Anyway, I will follow up what the previous speakers have mentioned, but I will focus more on CFBC for carbon capture. But initially, I would like to present my view of the background that was just mentioned by the previous speakers. 1.1 is that the Earth temperature is increasing because of CO2 accumulation, as well known. India and other countries have signed the Paris Agreement, which where we have promised to reduce the heating to a certain degree, to a certain limit. We have to our disposal various energy sources like solar, wind, nuclear energy, which can contribute to the reduction of the emissions of greenhouse gases. And I have noticed, although I don't know so much about it, that India has large resources of thorium, which is a fertile material which can be converted into fissile material to produce nuclear energy. I know that India has been dedicating itself for many years investigating this, but I'm not aware of the outcome or the prospects. I noticed from previous speakers that nuclear energy is supposed to be play a rather small role in the future development. But I just point out that thorium is available. Coal is also available, and that has also been pointed out. And in fact, then measures to reduce CO2 emissions from coal combustion should be investigated, and that has already been mentioned. Yeah, the question is how to capture and deposit these CO2 emissions. We will talk about it. Fluidized bed boilers play a significant role, and I'm happy about that. Of course, pulverized fuel can also be used for the purpose, but fluidized bed is very suitable for the Indian coals that was emphasized by previous speakers. Also emphasized by previous speakers, there are several options for CO2 reduction. Of course, combustion of biomass and biogeneous waste means a capture of CO2 if the biomass is replaced by new biomass. Co-combustion, the same thing. It is a partial capture of CO2. An increase of efficiency was also mentioned previously, and I think fluidized bed again is very suitable because it's rather even heat flux distribution in the furnace. So to build fluidized bed in the supercritical mode is less complicated perhaps than in a PC boiler. So that is a possibility to, according to predictions, to increase the efficiency of cold combustion to about 45%, but without CO2 capture in that case. Anyway, 45% is a good value. Then we have the CO2 capture methods. This is my focus today. The oxy-fuel, calcium looping, and chemical looping combustion. This is for total removal of CO2. So I start with oxy combustion. And there are two procedures for oxy combustion. Either the oxygen is generated by cryogenic air separation. That's the usual way to do it, at present at least. And then nitrogen is replaced by the recirculated flue gas. That is, again, the usual way in the proposed procedures that have been presented. But the other way should also be mentioned, that because cryogenic air separation is a rather expensive way to produce oxygen, so maybe other modes of oxygen production could be interesting. And here is one where a metal powder is oxidized, and this metal oxide is introduced in a reactor together with the fuel, and that is called the chemical looping combustion of in fluidized bed. So I will also talk about that later. First, oxy-fuel, the usual arrangement that you have probably seen if you are interested in the topic. You have a boiler here with all its equipment, including flue gas, heat transfer from the flue gases up to about, say, 150 degrees, where the flue gases enter some cleaning device, and it is cleaned. From here, it can be recirculated partially in the wet. It still contains moisture. It is recirculated and mixed with the oxygen produced by an air separation unit. Or the flue gases can continue to a condensation unit, which removes the water vapor, which is necessary for the CO2 treatment. So there is always a removal of water vapor. And the question is whether the recycling should take place after that removal or before. I think personally that the easiest way is to just remove it before the cleaning. Okay, so an even more simple way would be to use water vapor directly. I was very much attracted by this method, and I included it in my studies to see what does it mean. Actually, is it so simple and so advantageous as I thought from the beginning? And the answer is unfortunately no, because when I calculate the amount of heat needed to evaporate the water, it is, I thought it was a small amount, but it is the same amount more or less as is absorbed by the gases in the combustion chamber. So it is a major amount of heat that is needed to vaporize the water. And then it works, of course, but the water has to be removed here in this concentration unit. Now the amount of water is much higher than in a previous case. So this is also a tremendous amount of heat that is wasted. It can be removed, of course, by use of air, surrounding air, but it's a tremendous waste of energy. So again, it is not so favorable. One would like here to have a bottom cycle and to regain some electricity in such a thermodynamic cycle while cooling the gas further. But this is not a very good solution because it complicates the whole system, and then the advantages are disappear. So I think I have to say that so far I stay with this method, flue gas recirculation. But maybe I will investigate this further. Maybe there is some way to use it after all. We will see. Okay, so we have two aspects here as well for oxy-fuel. Either you can refit the existing boilers, or you can make new development of boilers. I'm talking all the time of CFB boilers. Since there are many CFB boilers in operation, it could be quite attractive if they could be simply retrofitted for CO2 capture. In any case, the basic data are gas temperature around 900 degrees centigrade, fluidization velocity around 5 meters per second, and some excess oxygen in this order of magnitude. All these data may be adjusted back and forth depending on the situation, but they are just listed here to give you an impression. Okay, the retrofit case. It is based on heat balance because you don't want to change anything. You just want the same conditions as in the air-fired boiler. And then you would like to know what is the oxygen concentration that corresponds to the operation with air. And you can calculate that by heat balance, and you get that with the CO2, the flue gas recirculation, you come to a value around 30% of oxygen. It should be compared with the oxygen in air, which is 21%. If we use water vapor, it would be somewhat higher. But this is unfortunately not the whole story. In the fluidized bed, well, in a pulverized boiler, it would be okay. But in a fluidized bed, you also have to satisfy the volume balance, because the fluidization velocity is supposed to be kept at the same value as during air combustion. But that is related to the volume flow. And since the densities are quite different between nitrogen, which is to be replaced by CO2, or the mixture between CO2 and water vapor, you get a different density, and then the fluidization velocity corresponding to the heat balance is not 5 meters per second. You have to manipulate the boiler in various ways in order to do this, and I don't know yet
exactly how to manage. I'm looking at this myself, and the question is, how much do we have to change the boiler to do this, to use existing boilers? If it is not possible, then this possibility will vanish, and we will focus only on the new developments, because new development is without a problem of this kind, because you can choose freely the fluidization velocity and the bed temperature. And if you have these two, you have the density and you have the bed density, because it depends on the fluidization velocity and the particle size, of course, but basically the fluidization velocity. The circulation rate is also dependent on the fluidization velocity. So these are given more or less. And the changes that you make then is the oxygen concentration. You chose an oxygen concentration between that of air and a high one. I have said 60% oxygen here, but I have added a mark of interrogation because nobody knows how high an oxygen concentration you can have. But I have to say that the fluidized bed is quite forgiving because of the high specific heat of the fluidized bed. It can absorb the heat of combustion quite well, and perhaps if the mixing in the bed is good, you can reach rather high oxygen concentrations. And I think this is a topic that needs to be investigated further. The problem when you increase the oxygen concentration is perhaps that, well, the problem, the advantage even, there's a smaller recirculation gas flow at the same time. And that means that the cross-section of a surface area is smaller. So the furnace becomes smaller. That means that the heat release per cross-section surface area is higher. But the consequence of smaller furnaces is that there is not so much space for heat removal in the furnace, and more heat removal has to take place in external heat exchangers. So if I compare with the corresponding air-fired unit. So that is a big challenge. Instead of transferring the heat inside the combustion chamber to a large extent, you can only do this partially, and you have to rely on external heat exchangers. I will show an example, but first I will just show you the calculation made. This is the mass flow, fuel flow, and the gas flow, including the recirculation flow. And that should be similar to the fluidization velocity times the cross-section and the density of the gas. So these two should be similar. And by means of putting these together, it is simple to calculate the difference between the circulation case and the air case, because they are related to these, which can be easily calculated. And the result is that this is the relative cross-section. This is the cross-section for air combustion. This is the oxygen concentration for air combustion. And this is what happens when you increase the oxygen concentration. You reduce considerably the cross-section of the furnace. I have extended this to 1 here, but this is pure oxygen. It's just a calculation, of course. So when maybe in a realistic case, we are somewhere here at 40 to 50% oxygen. Perhaps it is possible to go further. So this is a sketch of a circulating fluidized bed boiler with internal heat exchanger here. And this is a copy of a 300 megawatt Chinese boiler for 300 megawatt electric power with the dimensions of a Chinese boiler. But if we transfer this to oxy-fuel boiler, we get something like this.
a much smaller cross section, more narrow furnace, and the heat transfer surface we don't have space for the same amount of heat transfer equipment as we had in the other boiler, so we have to place some of the heat transfer equipment in the external heat exchanger in the circulating loop. So that is always possible, and this is a solution. I can say that so far I think this is a viable solution, and it needs technical experience and development, but I cannot see any restrictions except that the circulating flow has to be known. You have to know how much flow of particles are circulating. Okay, so we continue. My conclusion is that it's quite similar to existing air CFB boilers. The same technology can be used. For higher oxygen concentration, the furnaces are smaller. That's the advantages. Disadvantage is that the air separation is expensive with the method used so far. The cryogenic separation, which is used because it is a known technology. So other methods such as adsorption methods or oxygen transport membranes are possible, but they are not developed for the sizes required in large boilers. So they are mentioned and there are investigations made, but I don't know at this moment how well it is possible to use them. So that is the conclusion on oxy-firing. The other way to produce oxygen would be to oxidize a metal oxide in chemical looping combustion. We have two reactors coupled together, and both of them CFB reactors. This is an air reactor. Air enters and oxidizes a metal, which is called Me here, some kind of metal, which will become MEO, oxidized metal. And the gas is leaving nitrogen from the air and oxygen. Whereas the metal will leave in a more oxidized state than when it enters. So it includes another oxygen atom here, which is transported to the fuel reactor, where the fuel is added, and then the fuel is oxidized by the metal oxide, and the result is carbon dioxide and water vapor. Water vapor is removed by condensation, so we get what we want, the carbon dioxide, for deposition. This is too good to be true, but it has been shown, so it is possible. In detail, the chemical reactions could be written like this: a metal oxide reacting with oxygen to produce a more oxidized metal, and this more oxidized metal is reacting with some hydrocarbon to become a reduced metal oxide and CO2 and water vapor. If we add these two reactions, we get the ordinary oxidation reaction for this hydrocarbon. That seems quite simple. And it could be even more simple. This is an air reactor here. The below is a circulating fluidized bed reactor, and then particles are separated here and they go down to this fuel reactor here, whereas the nitrogen and excess oxygen leaves here. Well, in this case, it was fed by a gaseous fuel. So it is a bubbling fluidized bed here, fluidized by this gaseous fuel, but the bed consists of oxygen carriers. So here the reaction takes place and the CO2 and water vapor is produced. It is a joke more or less from our side, because this is it was proposed 20 years ago. This is our university boiler, the Chalmers 12 megawatt boiler, and we proposed to make this, but we unfortunately, or fortunately, I don't know how to express it, we didn't get the money, so we could never do this. In retrospect, I realize that this bubbling bed would not be very suitable because of the bypass of gas through the bubbles. So a more plug flow like reactor, like the circulating fluidized bed, would be better in this case. And that would imply 2 coupled circulating reactors, which I can, basically what I had shown here, but I will show it later. What we have then in this case that I just showed you was the gas entering here to be burnt, meeting the oxygen carrier and reacting to produce water vapor and CO2. It's okay, it works, and we have done it, but we think it is more interesting, challenging to use solid fuel, carbon powder. And here we use carbon. This is yellow. And it is fluidized. In this case, it is fluidized not with the gas, combustible gas, but with the water vapor. So what happens when such a fuel particle enters here? It releases its volatiles, and they do react with the metal oxide. But the char particle will not react, because particle-particle reactions are not very possible, very easy to achieve. So what we propose to do, or what is done, is to gasify the particle, and if the gases produced, CO and hydrogen, can be reacted by this metal oxide. It's okay, it works, but it is a slow reaction. Gasification is very slow. There are some possibilities here. This is another situation which is called CLOO, chemical looping with oxygen uncoupling. The uncoupling consists of this particular oxygen carrier, which is of such a kind that when it enters the fuel reactor, some oxygen atoms are released because of equilibrium conditions or such. And then these oxygen atoms react with the coal particle, and then it works much faster. So the conversion is faster if we use this CLOO. This is the manganese oxide, copper, and things like that. There are many oxygen carriers, and they have been extensively investigated. Reactivity is important, but cost is important, temperature resistance, and so on. You see, there are a number of oxides here that you recognize that can be used. They can be manufactured, and they look very beautiful. And this, like a powder that is added to the reactors. But cheaper would be to use the natural ore or waste material of some kind. For instance, iron ore or manganese ore. And one item that we like very much is ilmenite, which is a titanium, iron titanium oxide, or it can also include other metals. So there are possibilities, but one has to think of the cost particularly, and to recover, perhaps if they are very expensive, they have to be recovered to the reactor. Some problems are related. First of all, the solid fuel conversion is slow. I mentioned that, but it can be improved with this CLOO method. Some unreacted char may return to the air reactor and then produce CO2 in the air reactor, but it can be reduced by so-called carbon stripping. It's carbon burn-up on the way back to the air reactor. The volatiles may not, or the volatile gases may not be reacted in the fuel reactor, and they may escape with the off gases. But that then has to be arranged with what they call polishing. It has to be reacted with oxygen to reduce the amount of unreacted gases that could escape from the fuel reactor. However, I think this is a scale problem. So in the laboratory reactors, these are noticed very clearly, but in the large-scale reactor, they will be less important, and it remains to be seen in the large scale how important they are and what can be done to reduce them. Also, I mentioned that the separation of ash and metal particles could be of interest. The conclusion is that it is still under development, and its main advantage is that it is an oxy-combustion boiler which does not need an air separation unit. We have other methods, that is calcium looping. This is a flue gas treatment. If you know about the CO2 removal methods, there is one is the direct reaction, which is the oxy-fuel reaction, but the other is when you treat the flue gas. And usually the method is to use amine scrubbing of the flue gas from pulverized coal combustors. But these are also refined nowadays, so there are many amines and combinations that can be used. But in this case, in fluidized bed case, we use calcium, for instance, to capture the CO2, and that is called then the calcium looping. It is based on the fact that if you look at the equilibrium diagram here of calcium carbonate, which is limestone, then you have a CO2 concentration on this axis, and you have temperature on the horizontal axis. The blue curve is the difference between the two areas. In this part, calcium carbonate is stable. So if we add calcium oxide here, it would like to be converted to calcium carbonate. Whereas on this, at higher temperatures, we have a calcium oxide as a stable compound, and calcium carbonate will disintegrate into calcium oxide and CO2. That is the trick then, to carbonize the limestone by means of flow gases containing CO2, and then transport the produced calcium carbonate to the other side and react it there. So this is the looping aspect. It looks something like this, that here comes the flue gas from the boiler. This is a pulverized fuel boiler, or whatever, any type of boiler with a gas containing CO2. The CO2 is absorbed here, reacted here by the calcium oxide, which is produced in the other reactor, which is calciner. So there is a calcium oxide produced in the calciner, and it is carbonated here. And then the carbonated result goes back to the calciner, and it is calcined again like this. This happens at different temperatures, so we have to cool this part to 600 degrees, and this has to be heated. This is an advantage, actually, that we can extract heat at such a high temperature, because that can be included in the steam cycle. But here we have to increase the temperature to 900 degrees, and also this is an endothermic reaction requiring heat. So we have to add fuel here, but we cannot burn fuel in air, because then we would produce CO2. So it is it's burnt in oxygen, and it is combustion is moderated by flue gas recirculation. We have an oxy-fuel combustor here, but only half as large as the conventional oxy-fuel combustor for the same total power. So yeah, it's a tremendous thing. This is for 1,000 megawatt electric power coal-fired boiler. Very big hello. Very big calciner and a very big calciner and a big carbonator with their cyclones. So they are big. The problem is the size of the equipment, quite large. The other problem is the fuel has to be supplied to the calciner, 50% of the total fuel, and the air separation unit is needed. Heat has to be removed from the carbonator, but as I said, this is okay for limestone because it is at a reasonable temperature. But there are other materials that could be used, for instance, potassium or compounds and oxides, but they release their CO2 at a lower temperature, and then the heat cannot be recovered so easily. So limestone has a great advantage here. Yeah, there is another problem, also problems related, that the limestone can stand only a few loops, but then it loses its capacity. So it has to be replaced constantly. But fortunately, limestone is a very common species in the environment, so it is it's not extremely expensive. Yeah, I think I have concluded that. Yeah, I have concluded this. I think the overall conclusion is what remains for my time. And then I will say that, yeah, there are several ways to capture CO2 using fluidized bed combustion, and they are quite suitable for CO2 reduction. I think in many cases much more suitable than pulverized coal, because pulverized coal cannot easily use different oxygen concentrations, because then the temperature will be high and it will be difficult to manage. But in a fluidized bed, the temperature can be controlled, as I said, because of the moderating action of the bed. Not only the gases are moderating, but also the fluidized bed serves as a moderator. The methods are proposals. They are investigated in laboratories. And I think that large-scale pilot plants are needed to further promote the development. I hope you will make such a large plant somewhere in India, because India is a large country with a large amount of coal, and you really have a reason to spend some effort in testing the possibilities of using these methods that I mentioned. The Chinese are building some units. In Europe, it is more difficult for other reasons, but I think in India you have the possibility. It's interesting that CO2 separation and the preparation of CO2 after removing the water vapor, as I said, and going through a compression to produce liquid CO2 for disposal. This process contains possibilities to remove also at least nitrogen and sulfur dioxides. Mercury, I don't know, but this I know that they can be removed. So that could make the whole plant cheaper if they are removed in the CO2 compression unit. You don't need then the big nitrogen and sulfur dioxide capture equipment. But of course, in a fluidized bed, these equipments are, you use limestone to capture the sulfur, and by means of the organization of the combustion, you can reduce quite well the nitrogen oxides also. So maybe this is more for pulverized coal combustion than for fluidized bed. But nevertheless, it is possible to get a near zero emission. The method shown, they do involve an increased production cost. You cannot deny that. But you have to recognize that the global warming also has expensive consequences. I think we have not seen these consequences at present. Maybe we have seen them in an increased amount of instabilities in weather, like storms and various things that inundations that may happen. But it is not a real case. It will be worse, I think, when the temperature increases. So there is a reason that is motivated to spend more effort in this reduction, the CO2 emissions. Okay, so I think this is what it is not what I wanted to say, but it is what I can say in half an hour. As you know, if you know me, I can continue forever.
All right, thank you, Professor Lechner, for a very insightful talk on carbon capture. I'm sure that we have a lot of attendees today, and everyone will have several questions. But in the interest of time, we have decided to take the Q&A towards the end of the workshop. That is when we have our panel discussion. So during our panel discussion, we'll take up all the questions. I request all the participants of the workshop, if you have any specific question, to put it on the chat window so that we can record it and we can address them during the panel discussion, which will be towards the end of the workshop. So I hope you understand that because of the time constraint, we have to do this. So, so now I would like to move on to our next speaker. Our next speaker is Professor David Pilares. He is an associate professor in the Department of Space, Earth and Environment, which is Division of Energy Technology in Chalmers University of Technology, Gothenburg, Sweden. He's also one of the co-PIs in our project, sponsored to SPAR. Professor Pilares will be talking about biomass co-firing in CFBC, and he'll mention some of the state of the art in this area. Professor Pilares, it's up to you. Stage is yours.
Thank you very much. Am I audible, and are my slides visible?
Yes.
Okay, thank you. So thank you for this introduction, and as it was said, I will be presenting at least some of the main features of biomass co-firing in circulating fluidized bed combustors. So first, some definition, very basic, and what is the definition and what is the purpose of co-combustion? And well, it is simply that you have fuels of different types being converted in the same furnace, in the same boiler system. Purposes of this, it can be, so to say, spontaneous, non-forced, no political action needed, and it's simply that you have a fuel which is available, which typically is close and available, and it's cheap. So there is an automatic, non-forced economic drive for that, and this occurs in some occasions. Another purpose or situation can be the substitution of fossil fuels, and then typically what is needed here is political action or some marketing action. So in this way, a certain operator or a certain industry can get greener by reducing CO2 emissions, atmospheric CO2 emissions on a net basis, by then substituting fossil fuels with biomass and renewable fractions of waste. And finally, another one which is also suitable is waste reduction, so handling these piles of waste that we have for energy utilization. So instead of just having a pure destruction of waste, to do something useful of it, and that would be then for co-combustion. Please note that these purposes, they are not complementary, so they can overlap. In some situations you can have the three of them at the same time. So let's have a look first at the fingerprint of some fuels. When we talk about having different fuels in the same system, what are the main properties of those fuels? What are the challenges then that they will have? If we look at bituminous coal. As you know, coal can have a wide range of ranks, but if we take bituminous, then we would have a volatile matter of about 35%. In this case, if we take the dry ash-free basis, then bituminous coal would be something about 40% in mass of that basis. And this can rank a lot from, of course, anthracite to lignite and so on. But here you can see the contrast of this mid-rank coal, bituminous, compared to biomass, for example. So in biomass, we have that the fixed carbon typically will lie below 20% in comparison to coal. And then the ash content typically will be much, much lower than coal. And of course, this different distribution of the energy content in the fuel between volatile matter and fixed carbon will have consequences and will mean that the combustion process will occur in different ways inside our furnace. I was referring earlier to this CO2 reduction, and here we can see how this is explained. So we have for the dry ash-free basis, 83% of carbon in this bituminous coal. It gets higher if we go to anthracite, for example, more higher rank coals. But if we look typical biomasses, they are around 50%. So in here, then we can see already a carbon content which is lower. So more on the same basis, we will have less carbon on the same energy basis and more hydrogen. We also can see a difference, of course, in sulfur. So the biomass is not containing that much sulfur as coal, which is, of course, an advantage in terms of emissions. And also we see some levels of chlorine, which typically, not always, but typically can be lower than coal. Speaking about CO2 reduction, this is a very rough figure, but it can give us an idea of how much is that energy reduction. So we have on the y-axis the CO2 emission, specific emission per energy unit. And what we have in the x-axis is the efficiency of the plant that we are looking at. So it's net efficiency on the basis of a lower heating value. We have the average in Europe here, somewhere between 35–40%, depending on the age of the plant. CFD technology nowadays is able to deliver the efficiencies around 45 or so. And then we have supercritical 1-3 units, which can get much higher efficiencies. But if we look here and on the CFB basis, if we go from a monofuel coal-based operation here, we would have this level of CO2 emissions per kilowatt hour generated. And you see here, if we introduce only 20% of biomass co-firing, then we are decreasing CO2 emissions quite much. We're going down by about 15% or more. So this is one of the main drives then on having co-firing. And this can be a rather mild measure. We are not speaking about substituting the whole thermal input from fossil fuel to a biomass, but just to have a share, a small share, 10, 15, 20%, and it can make already quite a large difference in terms of net atmospheric CO2 emissions. So why CFB? This is, of course, so far it's co-combustion and it's generic. I'm not focusing on any specific technology for this conversion, but why is CFB suitable for this? Well, mainly 3 reasons. One is high fuel flexibility, and this is one of the main features of fluidized bed units, that they have a very high flexibility in terms of fuel. This means that you can feed different fuel types without needing to worry much about the performance, the features of the process inside the unit. It will most probably handle it without any major problems. The only thing you need to make sure is that you are feeding the same thermal input so that the thermal balance of the unit, the heat balance, is still fulfilled. So this is one of the main features of fluidized beds. And it is of course a key feature when we are speaking co-combustion. This gives you the ability then to adapt your operation to the fuel market prices, for example, or seasonal variations or availabilities of different fuels. So you are not locked to a specific fuel. You don't need to sign long-term contracts with a certain fuel delivery, but you can adapt yourself to the market and to what is best suited in the different seasons or situations of the market. So this is one of the main drives for fluidized bed technology. Another one is that no fuel preparation is required, or no major one. We don't need to have grinding or having fine powdering of the fuels and so on. It's rather simple. So you just need typically chipping, and that's the shape or the form in which biomass is typically delivered already at your plant. So that is also an advantage. And finally, we have synergy effects. What we have here is that these fuels will be mixed. The different types of fuels will meet each other. There is a very strong mixing inside fluidized bed units, so they will meet each other. We don't have separate burners dedicated to the different fuels, but all these fuels will together share the same environments, and this will create interactions, interplays between the different fuel types. So if we are alert into this, then we can look and seek for these synergetic effects, which can lead to lowered emissions, to increased efficiency. And I will talk later about how it can be beneficial to have co-combustion. For example, you have some risk when it comes to, for example, biomass, mono-combustion of biomass. But when you do co-combustion, then these risks are in principle are removed. So co-firing can be a beneficial way to have a safer conversion of certain fuels. So these are the main three advantages of fluidized bed technology. Before we go a bit deeper, I would like to show an example of a front runner, and this is here a Scandinavian example. This is the largest biofuel plant in terms of thermal input of coming from biofuel in the wall, and this is in Finland. So it produces, it produces a 550 thermal megawatt of steam. As you see here to the right-hand side, this is then used to produce power, 240 megawatt of electricity. And then we have still 100 megawatt left for steam and 60 megawatt for district heating. So what about the fuel mix for these? Well, you have here the shares for this, and you have here that biofuels are making up for about half of this thermal input, and then the rest comes mainly from peat, and then you can have for full load and for startups you can have some or for low load burners you can have coal or oil also 10%. The important thing here is that what peat is considered as. There are discussions on how peat is to be considered, if it is renewable in some sense or not. It's somewhere in the boundary region between fossil fuels and non-fossil fuels. So there is a debate about peat. How is that to be considered? But if we look at the biomass share, at the renewable fuel share, as I said, it can get up to 50% in this unit, and 50% of this power is 225 megawatt thermal megawatts, and that is very much, and that is, I would claim, almost like the natural limit for the use of biofuels, because biofuels, they have an energy content per volume and per mass which is lower than fossil fuels, than coal, for example. So transportation issues make it an economical challenge. So you can typically not transport a lot of biofuels into your plant. One rule of thumb is that about 100 kilometers, distances longer than 100 kilometers are the ones that are stopping the larger shares of the use of biofuels. So I would say that this is more or less where typically the limit goes, and this about this just above 200 thermal megawatts. So this is a good example. It has been operating for about 20 years now, and it operates very finely. And as I said, it's one of the main reasons to the low CO2 net CO2 emissions of the Scandinavian regions. Then, and then just not to tell you that co-combustion is just a walk in the park. I would just would like to strengthen 4 aspects that we need to consider that can be a risk, but if we are aware of them, then I will try to show that we are able to handle them. This technology is able to handle them without any major issues. So it will be the heat balance, the maldistributions within the furnace, the emissions, and then some ash-related issues. And one could speak for hours in each of these, so I will just make a very, very short summary of each. The first one is probably the heat balance, is probably the shortest one, because this is a concern that people may have when I change my fuel. How will my heat extraction vary? Well, what we have here is typically in large scale, utility scale CFB units, heat is extracted from the furnace walls. Typically also there is some heat extracted from the cyclone walls and even some external heat exchangers here from the loop seal. And this is the hot loop extraction. Then of course you have a convection path where you extract heat from the flue gases. Note also that as we grow in scale for these units, we need to add some extra heat extraction surfaces here inside the furnace to compensate for the scaling effect. So this is how it looks. And of course, from a thermodynamical point of view of your water side or steam side cycle, you would like these different heat extractions not to be modified much when you change fuel. That is a risk. You have a system which is in equilibrium, it's designed to operate in a certain way, and you would like those different shares, extraction shares, for the different evaporator superheaters to keep more or less constant, to not be affected by a change in fuel. So what happens in fluidized beds when we make a change in fuel? Well, not much, and I will try to explain shortly why. And the explanation for that lies in the concept of heat capacity of a fluidized bed. Professor Lechner was talking shortly about this in his presentation. Let's imagine this. Let's imagine a tube reactor in which we have pure hydrogen and then we are combusting it with oxygen. And of course, what the temperature will look like, the temperature profile will look like here, will be a sudden increase by this highly exothermic reaction that would look like this. Well, this is typically what you would have in burners or so on. What you have in a fluidized bed is an enormous amount of mass, which is the share of mass is in the solids, in the bed material itself. So you will have everywhere in a CFB solids, which will dominate the mass. This will create heat capacity. So if we take the same problem, but now we add a flow of solids, inert solids that are also flowing with the gas here, how that will temperature profile, how that will look like? Well, it would look something like this. We will have a very smooth or very small temperature increase because of this heat capacity effect. So this heat released here by this reaction, it has to heat up not only the gas flows as in this situation to the left, but also the solid flows. And this creates this very relatively small increase in temperature. So this is one of the main features in fluidized bed units, that we have a so-called thermal flywheel effect created by the solids. And this yields then a relatively homogeneous temperature fill all over the circulating loop. So making a modification anywhere in this hot loop will have an answer, so to say, in the whole loop. So the whole temperature fill will look rather homogeneous, and a difference, a local difference in the heat balance, extracting heat from somewhere, you will be able to notice it in anywhere in the loop, but that difference, that modification will be on the other side very, very slight. So this tells us that the extraction flows are not significantly modified by the fuel mix. So this is very good news for our steam side, because it means that if we change fuels, temperatures, as long as we're putting the same thermal input inside, the temperature distribution all along our hot loop and over the different heat extraction surfaces will look very much the same. And that is, as I said, very good news. Then it talks, or it is telling that we will have a stable system. So this is good. The heat balance is not a problem, and this is corroborated, confirmed by operation and experimental experience. Then we have maldistributions within the furnace. I'll try to give some short background into this. So what we have in a bed technology, in contrast to what we have with burners, is that in a bed technology we are feeding fuel from one certain location, but our oxidizer, our oxygen with the air, is typically well distributed over the whole cross section. So then the question is, will the fuel manage to spread, to mix laterally fast enough so that it can meet the whole oxygen? And of course, this becomes critical as we grow in size. So for small boilers, this is not a problem, but as we go to very large scale, this can become a challenge, of course. And then we would like to have fuels that mix very fast or that convert relatively slow. And there is some dimensionless number describing this. This is the Damcolor number, which compares the kinetic rate to the transport rate. So typically with situations in which we don't have a very fast mixing, or our fuel is converting very fast, we will have situations like this with fuel concentrations which are not that homogeneous over the cross section. But on the other side, if we have a good control of this, we can mix our fuel fast enough, or we can delay the conversion of the fuel enough, then we will have nice situations in which there will be a very homogeneous distribution of our fuel. The Damcolor number can also be expressed in terms of characteristic times, but then it is reversed compared to the kinetic rates, of course. And if we set Damcolor numbers in these two extreme cases, we will have the high values for the left case and the low values for the right-hand case. So we have this, and from this we see then that the kinetics, the characteristic time for the kinetics, is important. If we then relate this to the combustion of solid fuels, what happens with the solid fuel? Well, we have the fresh fuel. It heats up after insertion, after being fed into the unit, and then it releases water as it is heated up. Then we have the dry fuel. Further heating of this yields char, and it's the volatile release. This is devolatilization. And finally, of course, these volatiles will burn with oxygen as they meet oxygen by homogeneous reaction, and they will release heat. And for biomass, most of the energy content is here. So this will be the main mechanism for release heat when burning biomass. And this char that we have left, of course, will meet also this oxygen, and by heterogeneous reactions, it will also release heat. And this is the main mechanism for heat release for coal high rank fuels. Well, again, related to the kinetics that we were seeing in the former slide, this process, devolatilization, is relatively fast. I mean, typically below 1 minute. It can take typically 20-30 seconds, while char combustion, it is in the order of several minutes. So this will take a long time, char combustion, while devolatilization will be a matter of some tenths of seconds. This means then that, of course, we will have a more challenging situation for the volatiles. The mixing rate will be the same. We can more or less, we can assume that the fuel will mix equally fast at the different stages of conversion, but the kinetics will change. So the drying will be very fast, the devolatilization some tenths of seconds, and then the char fill is relatively slow then, some 10 minutes or so. So this means then, relating again to the Damcolor number, that fuels that rely a lot on the volatile matter for their energy release, they will tend to create this situation much more than fuels that rely on the char, on the fixed carbon. And this is the case for coal to the right, and here for the volatile matter, this is more the case of biomass. So here we will have to be alert then that our feeding of biomass is not creating a too strong maldistribution of fuel releases. We have been running some experiments, of course, at the Chalmers unit and some modeling of it. Here is the oxygen concentration for the anthracite case. So very nice, very homogeneous cross-sectional distribution of the oxygen concentration. While here for the wood case, if we are feeding from this side, so Y, negative Y values, we see that the oxygen is depleted here, while on the opposite wall where we are not feeding fuel, there is still oxygen left. If we look at volatile matter, it can look like this, and notice the different scales. There is much more volatile matter for the wood case. And finally, if we look at experimental values from the Chalmers boiler, here we have a case with pure coal, and we are feeding from this side, and this is the CO measurements at 9 points over the whole cross section. So we see that there is more CO here close to the fuel feeding. That's obvious. There will be less oxygen here, more presence of fuel, so less oxygen available. But if we feed 50% wood in terms of energy content, then we see that this maldistribution is accentuated by the use of wood. Then we have much more CO close to the fuel feeding point. Of course, there are measures to counteract this and to solve this with injections of secondary air. So it's the secondary to primary air ratio can be modified to handle these situations then. And this is what we see here then. For the anthracite case, we have a very nice, very smooth temperature field, very, very homogeneous here. As you see, it varies just some 20 degrees or so over the whole domain. While for biomass, we have this release of volatiles, and here we have the secondary air injection. And when this secondary air meets the volatiles, then it creates this increase in oxygen. It is an increase which is not very extreme, because again, we have the thermal flywheel effect, but still much more noticeable than the one for anthracite, of course. So this is one aspect to consider, but again, it's not critical thanks to the thermal flywheel effect in fluidized bed units. So we are fine with this also. And then we can look into emissions, and I will talk about synergy effects. And what do we mean by synergy? Well, the way I like to look at it is that if you have two fuels combined and operating solely with fuel A would leave you this value here, and solely with fuel B would yield this value here, then all values following in this line means that there is no synergy, while values deviating from the straight line between these 2 points will indicate that there is some kind of interaction, of interplay between the two fuels. And
excuse me,
David, you got muted. Can you unmute yourself?
Yeah, was this last slide or?
Yeah, just yeah.
Yeah, we'll just take it very shortly again. So yeah, just to define that when we are burning solely fuel A here, and we would yield this value of some emission, and fuel B, and we would yield this value, then all points of co-combustion falling on this straight line will indicate no significant interplay between those two fuels, but are simply the expected values, while values deviating from the diagonal line, either below it or above it, will indicate that there is some interplay between the fuels. And yeah, I was saying that the different fuel properties can have effects on different mechanisms. This is a scheme here that is telling us about the different fuel elements and how they affect different mechanisms. But we look at some examples. If we look at carbon monoxide, for example, we see then that when we have wood, of course, wood has less carbon content, so there will be less of that carbon monoxide emissions than coal up here. But when we have the different mixtures, fuel mixes, with the two, we see that they follow rather much this diagonal line. So not much to be said there about interplays. The same goes for sulfur then. Almost nothing in both, a lot in coal, but again, they fall on the diagonal line. It is the opposite case then for all nitrogen-related emissions. Here we have nitric oxide, and as we see, they don't follow the diagonal line, the straight line, but what we see is that there is an interplay that is increasing then the NO emissions. And this has to do with, both the char content, the char inventory in the bed, and the local temperatures. The same, but applies then to nitrous oxide, but here what we see is a slight decrease, so a beneficial effect here, slightly deviating from the diagonal line. And finally, ash-related issues, and this is, I would say, the phenomena that people are most afraid of when you are doing monocombustion of biomass, of biofuels, so boilers that are burning solely biomass. And it's this agglomeration, this sintering, and this means that your ash gets sticky and sticks together, and in the end it risks to simply solidify, and then it will of course cause a stop in your operation, and you will need to let the whole unit cool down and get into it and remove all these sinterings. And this is of course devastating for the operation and your revenues. You need to stop the plant, and this can take days or weeks then in total. So these sinterings, they look like this. Here you have bed material which has sintered together, and in operation you can see it like this. So if you are measuring, monitoring the pressure drop, you will start seeing sudden drops in the pressure drop, sudden fluctuations. So this is one way. There are attractor theories developing methods in order to try to predict agglomeration before it is too late, so to say, and try to take action on it before it is too late. So this is just a observation. It happens. People do not want this, and it happens for combustion of solely biomass then. What causes this? Well, here we have the main originators of it. So it has been correlated to the contents of calcium and silica in the fuel analysis, but mainly the ones that one should be looking for are these sodium, natrium, and potassium then. And these are the ones that one should look. And as we see here, straw is high contents of this, and typically straw is the one always tending to agglomerate much more than, for example, wood chips or so. So it's always important at the fuel analysis to look at these alkali metals. Another thing is important is that the content, the mass content, doesn't tell it all. If you look at coal, they will also present some potassium, for example, but it has a different form. So the content itself doesn't tell it all. It's the form it takes. And in biomass, it takes the form that it's released in a way that it can create agglomeration. One nice thing is then to use co-combustion as a solution. So if you are burning pure biomass and have this problem, it was shown in our boiler then that if you add 2% of sludge, only 2%, it solved the problem actually. So here you could have a steady operation without any problem just by adding 2% of sludge. And then was this further studied, and we saw that, okay, with pure biomass, the agglomeration was occurring at this temperature, just above 900 Celsius. But the more sludge we added, the more.
David, you got muted again. David, sorry, you got muted again.
I don't know what happens. I'm sorry.
You were on the slide. Yeah, you were on the slide.
Yeah, okay, yeah, so exactly. So when we operate with pure biomass, agglomeration tends to happen at very low temperatures already, but the more sludge we feed, I was showing this 2% example on the former slide, but if we increase the feeding of sludge, then we can operate at higher temperatures before we can see some agglomeration. So this is an example of a good synergy of co-combustion then. Looking at what happens, the explanation for this, of course, then one could have some electron microscope studies, and what we saw then is that when having sludge, there was this layer here. So this is the sticky layer that typically would have created agglomeration. But what we saw then is that this layer, the sticky layer, was coated with another layer of alumina, iron, and phosphor, which was preventing then agglomeration then. So this is one example of beneficial, so to say, effects of co-combustion. So I've gone shortly through this, and as I said, the heat balance is not a problem. Maldistributions within the furnace are not critical thanks to this thermal flywheel effect. Emissions, most of them are not affected. There is no strong interplay, but for nitrogen-related ones, there is some interplay, but still very moderate. And finally, we have ash-related issues for biomass, but typically, I mean, if you have the majority of fuel being coal, adding some 10% of biomass is not being a problem at all. So that should be also be on the very safe side. In general, just to say that then we are in a relatively safe margin, so to say, to incorporate biomass at utility scale, and this is what has been done here in Europe. This is in Poland. So this is a project that took place in Turów Power Station. This is a huge power station in the order of or above gigawatt scale, electric gigawatt scale. And what was done here is to feed some furnaces here with different shares of biomass, I think up to 15–20%. And it was showing good operation with no problems at all. So it showed that it's something which is doable, and it's a way to retrofit existing plants running on coal in a way that they then can lower their CO2 net emissions. So as a final sum up, co-combustion in CFB boilers is a cheap method for CO2 reduction. It can support variations in the fuel, whether they are seasonal or economical. Waste can be utilized, and this is very beneficial, typically from an economical point of view also. This is typically a very cheap fuel. So if you can handle it, you're solving someone else's problem and you are benefiting from it. It's a fuel in the end. And it's a way to convert biofuels waste with high efficiency and with efficient flue gas cleaning. And finally, as I said, these 4 potential pitfalls that exist, I have tried to summarize that and show that they are very mild or non-existing or very mild and can be easily handled then. And this was all from my side. Thank you so much for your attention.
All right, thank you, Professor David. I think it was a really good talk on biomass co-firing, particularly the insights on handling of biomass and its burning characteristics, which were very, very interesting. Thank you for your talk. So our next speaker is Mr. Timo Eriksson from Sumitomo SHI Fosterville. Mr. Timo would be talking on clean coal technologies for India, and he will provide some views on the future of CFBC for carbon capture and biomass co-firing. So Mr. Eriksson.
Okay, thank you. Thank you very much.
All right, thank you.
So this presentation will concentrate mainly on the CFBC use for biomass co-firing, biomass standalone firing, and also carbon capture possibilities. So if the target is to cut CO2 emissions, we have, of course, many different pathways to fulfill that, but here we discuss three different approaches. First one is application of high efficiency steam cycle and a supercritical ultra supercritical CFPC. And the second one is using CO2 neutral fuels, either via biomass co-firing or standalone biomass firing. Then the third one is to apply CO2 capture and storage or utilization, and in this case through oxy-fuel CFP combustion. Starting with the high efficiency steam cycle approach. So obviously, when we apply higher steam parameters, then the net plant efficiency increases clearly. So this is not the only benefit to have a higher efficiency, but it also means in reduced air emissions, reduced fuel and additive consumption, water consumption, and generation of different wastes. Nevertheless, as nowadays there are various limits for CO2 specific emission, these tend to be hard to meet with a high efficiency only, without CCS. Anyway, this is showing a scale up of the SFW CFP technology with high steam parameters. We started from very small scale in the 1970s, then have been going upwards in coal-fired units, and now the biggest one is 2,200 megawatt electricity in Samcheok, Korea, with ultra supercritical steam temperature. Then on the biomass side here to the right, also there the scale has gone up. So far the biggest operating unit with biomass only is a 205 megawatt electricity unit in Polaniec, Poland, and now this year a new unit will be starting up in UK, Teesside, with 299 megawatt electricity biomass only. So there has been over 40 years of technology advancement, and we have supplied over 520 units globally with CFP technology. This is showing the geographical spread of sold units of different technologies. So it's quite widely spaced, and there are over 90 units in India. Actually, most of them have been supplied by our licensee EastCheck. Then a typical configuration of our supercritical CFP boiler, which has been applied or can be applied for different coal ranks, coal washery rejects, pet coke, and even 100% biomass of rather high quality. Then the design has to be optimized for each fuel mixture. But furnace is here in the middle. It's a Benson vertical evaporator. Then we have solid separators here on the sides, a big furnace on both sides. Final superheaters and reheaters we have in Intrex units. Then we may have some Platen superheater or reheater inside the furnace, and then we have further superheaters and economizers in the convective section, as well as a rotary up reheater. Then, depending on the fuel and emission limits, we may or may not apply either slip catalyst to take care of ammonia slip or a full SCR for the NOx. And this is showing the biggest unit so far, 4 times 500 50 megawatts electricity boilers connected to two 1100 megawatt turbines. The plant is owned by a Korean Southern Power Company, KOSPO. Steam temperature in both in superheat and reheat side is 603 C, and it is boilers are designed to burn mainly these are subbituminous coals of varying moisture, ash content and sulfur contents, but typically Indonesian coals, also others, and they can co-fire some biomass also. And these do not use any scrubbers for SOx. They are all in commercial operation, and the first one started in December 2016. And that's a photo of the plant. Then moving on to the biomass co-firing, we just heard a lot of it, but I'll try to cover also some different aspects. Well, in brief, CFP boiler has many advantages, specifically for this co-firing application, as we heard already, that as we have a fairly uniform and low temperature levels and a huge mass of circulating solid is balancing the process. So this is kind of a ideal technology for such applications. And okay, even this one we have already seen, but why co-fire biomass? Yeah, CO2 is one target and motivation for burning biomass, but it has been done long before discussion about CO2 started. So the reason is that typically biomass is locally available, and it may be a kind of a reject available for cheap price. And then co-firing, in one aspect for it is that it can be done in big boilers which have a high efficiency. This means that also the biomass will be burned with high efficiency for power production. Then biomass may replace field firing, causing environmental problems in many parts of the world, and gain energy at the same time. Then co-firing approach matches well with the seasonal supply of biomass. And you can balance the fuel input by the main fuel when needed, that there is not available biomass so much. And well, yeah, CFP boilers have traditionally been actually multi-fuel boilers, so that the one boiler burns many different kind of fuels, and the fuel supply may be changing all the time. So biomass firing has been very common, and biomass co-firing from the beginning. The situation has been a bit different in Northern Europe compared to Asia, for instance, that in Europe, typically biomass like bark, sawdust, and what other wood residues are burned together with peat and sludges, and often when these other fuels and BFP boilers are also applied a lot because of the lowest investment cost, then CFPs are used for the bigger units, and when higher fuel flexibility and higher steam parameters are required. In Asia, coal has often been included in the fuel mix together with secondary fuels. Besides these biomasses, also RDF, tire-derived fuels, sludges, and so on. And in these cases, the very wide variation in fuel properties favors CFP. Now, if you look at the different fuels, all of these have been burned in CFPs, but the trend seems to be that the favorable fuels are become more and more of waste-derived origin, and so different process rejects, agrobiomasses, and also wastes. So this fuel flexibility enables a transition to low or even negative CO2 power generation, even when coal has an important role. Then about these fuel mixtures, interactions of ash-forming elements, they have to be taken into account in multi-fuel combustions, because these interactions, they can be advantageous, helping to burn mixes, or they can be kind of fatal, resulting, for instance, agglomeration, as discussed just a few minutes ago. So this big mass of circulating material we already discussed, and then we have this talking about coal ash. It has a lot of sulfur and aluminosilicates, so those help to mitigate these agglomeration, fouling, and corrosion issues when we want to coal-fire biomass and waste fuels. So there will be less alkali chlorides and less low-melting alkali silicates. And talking about India, high ash coal is generally very good for coal-firing. Besides this chemistry, also physical properties have to be taken into account in fuel handling and feeding systems, so that the physical separation of different type of fuels does not happen and cause unstable operation. Then if woody biomass is the main fuel, coal-firing can also be done then, but then it is not equally good for instance, burning agrobiomass, because it's more than causing a dilution effect, not having these positive effects of the ash as that coal has. And for instance, a mixture of wood and plastics could be highly corrosive. Sludges, as mentioned, can have beneficial effects, but other types of sludges may also cause, for instance, corrosion problems, as there are some high chlorine sludges also generated in some processes. So Indian coal ash could be very well suitable for co-firing of, for instance, rice straw and RDF. But then besides co-firing, also biomass combustion in 100% share is common, has been done for a long time. Only the scale has increased, and the use of biomass in energy application is increasing in the world. Traditionally, biomass was used more locally, and the local availability of cheap biomass also limited the plant size. Now, international market for biomass has opened up, and that has actually also increased the scale of biomass units, in addition to different subsidies. So the quality of biomass, it's also expanding to more to recycled fuels and agricultural biomass. Altogether, we have supplied over 200 CFP and BFP units for firing biomass fuels. This is trying to give some kind of idea of biomasses traded or available in different parts of the world. So it seems that the trend is that as economics is of course important besides availability, then agricultural byproducts and fast-growing trees are gaining more popularity, which is not making things easier for technology vendors. But new challenges can be met. So we have already a very wide experience of different biomass fuels and have done numerous analysis, and we have developed models for predicting different issues such as agglomeration, fouling and corrosion deriving from the fuel properties. So this is trying to illustrate that how wide variation we have in agglomeration, fouling and corrosion between different fuels, like coal and peat are representing very easy fuels. And in the other hand, we have RDF, often lower quality recycled woods, and also some agrobiomass can be highly challenging fuel. But yeah, besides analysis and modeling, there are different approaches that we can use to predict the issues and solve them and design boilers that can use these fuels. So one important method is, even today, is a pilot plant combustion tests at the facilities, and then also different kind of smaller scale tests. So we do this kind of analysis and risk evaluations and utilize different kind of calculation models then to assess the challenges and find solutions for the challenges, and then make the design accordingly to achieve reliable operation, but nevertheless cost-effective design. Then just quickly going through some recent references of biomass combustion. This is in Finland, Lahti Energia, Kymijärvi. This is a 55 megawatt electricity boiler, 540C, designed to burn up to 100% biomass, meaning wood, and 100% peat and 100% coal. And these have all been demonstrated, but in practice the plant now runs on 100% biomass, and it is in commercial operation. Then another one in Sweden. It's also designed to burn up to 100% recycled wood and 100% forest residues, but in practice it is running mostly on 100% recycled wood, and it's also in commercial operation. The size was about the same as in the previous one, but the fuel is so waste-derived recycled wood. Then the next one that will be the biggest biomass only firing unit. We start this year in Teesside, UK, 299 megawatt electricity, and with a reheat steam cycle 568, burning mainly wood pellets imported from North Americas, I believe, or then mix of wood pellets and local wood chips. Then a totally different approach is based on CO2 capture, and in this case with oxyfuel CFP combustion. Then this is a technology that allows either near zero CO2 emissions with fossil fuel firing, or even negative CO2 emissions if we co-fire or fire totally biomass, which as such is considered CO2 neutral. So this could play a big role in trying to achieve these global targets of decreasing the warming. And it's very effective to go very low in CO2. Well, about this oxy-fuel combustion, there has been a lot of activity in that area, but this one shows a pilot plant that has been constructed and operated for fairly long periods in Spain at Sweden. And there in the heart of that, there is a up to 30 megawatt thermal FlexiBurn CFP boiler. FlexiBurn referring to something that can be operated both in air firing mode and oxy-fuel combustion mode. And in this case, this unit has also two different modes. That in the FlexiBurn modes, it's about 15 megawatt thermal. Then in a high oxygen mode, it runs up to about 30 megawatt thermal power. And this Sweden facilities included also experimental rigs for CO2 transport, and there was also CO2 processing unit. And then there's some distance apart, there was also a CO2 storage test facilities in saline aquifers. Then together with Sweden and the main partner Endesa Power Corporation, we developed or had this project of Oxus CFP3 Compostilia, where we did a feed front-end engineering and design study for a 300 megawatt electricity boiler and power plant to be built in Compostilia, Santiago Compostilia area in Spain. The boiler, this unit would also be such that it can run both in oxy-firing mode and air mode. And of course, the oxy combustion mode means reduced efficiency, as a lot of electricity is used for air separation and also CO2 compressors. But CO2 capture ratio would be over 5%. And it was calculated that over 5 million tons would be captured in the first 5 years. So the technology is considered ready for this phase. Nevertheless, it has not proceeded to this yet due to lack of commercial motivation, I would say. As you notice, there is this loss of efficiency, which is quite kind of inherent, but that can be reduced by connections to different processes. And for instance, one very simple way of improving the efficiency is combined heat and power system, as these systems generate a lot of heat. But then there are also other possibilities that you can connect these to, for instance, oxygen production from other processes, from renewable power generation. You could get, in a way, kind of free oxygen. And then there could be connections to various heat storages. And these kind of connections are being considered and studied further. Talking here about clean energy hubs. Then something about the future of CFPC in India. One of the salient advantages of CFP combustion is the capability to achieve low emission levels with fairly easy methods. So, for instance, NOx limit with SNCR with no catalyst, SOx without a scrubber by limestone feeding, and okay, outside this presentation, it's also possible to integrate the CFP scrubber with the backhouse system to further enhance the utilization of the limestone fed into boiler. It is a simple system to get the most out of the limestone. Then, okay, particulate matter is, these systems are very efficient today. Then CFP technology has emerged as the most favored steam generation technology in recent times. This was an announcement by Ministry of Power India, August 2018. And CFP technology is seen as the most favorable for India's utility power future in coal-fired power plants. As said here, the scale has gone really to big, large units, and even larger could be realized if find necessary. Still expanding a little bit outside these aspects already discussed, there are some development needs listed here. Here is a decarbonization problem to solve. Then we have a fluid aspect technology, the benefit, and then the development needs and next steps and the sector served. So if talking about power supply in coal-bound countries, then we have ultra supercritical fluid aspect for coal, and as well this oxy fluid aspect combustion with a carbon capture or carbon capture and utilization. The first one is commercially fully available, but still there are some development needs and things to improve, of course. Then oxy-combustion is waiting for a commercial demonstration. Then this dispatchable and reliable heat and power supply. Here we have all these fluid aspect and CFP technologies available, and carbon capture and storage. In addition, mentioned here is fluid aspect gasification of biomass for gas to power, which is also something that could be already done and has been already demonstrated, even though not discussed in this presentation. Then biofuels production to replace fossil fuels. This is also one area offering multiple opportunities, but this CCU here means when talking about oxy-combustion, instead of CO2 storage, we can use this CO2 further, for instance, combine it with hydrogen from renewables, make, for instance, methane or methanol used as transport fuels. Then there are different biochemicals that could be manufactured with a corresponding approach. Then we have a recovery of raw materials from industrial residues, byproducts, and end-of-life products. Well, here we have a fluid aspect combustion integrated with other processes, something under development. And then a very important role for boiler and combustion-based power generation will be in the future, which we already see today, is that these units can provide dispatchable power, meaning they can control the output, while renewables typically cannot when talking about solar and wind power. So I think I have now used my time, and so time to thank you.